Hi, everyone. My name is Max Bremer. I'm a postdoc in the computer architecture group, and I'll be talking about speeding up the simulation of computer architecture using parallel discrete event simulation. So to motivate this work, we really need to talk about the end of Moore's law. So what is Moore's law? Moore's law is this techno-economic law that for the past 60 years basically stipulated that the performance of computers would double every 2 years. And now we're hitting hard technological limits, things like we can't make transistors any smaller, we don't want to build giant power plants next to supercomputers, that are making this trend come to an end. And so as computer architects now, we have to go back to the drawing board and come up with new architectures that can maybe more efficiently leverage where transistors are placed to come up with the next generation of computers. Here I have two kind of proposed solutions. These are both AI accelerators, and they all have thousands to hundreds of thousands of cores. So there's really two trends here that are really standing out. So first is specialization, and the second is this massive concurrency. So specialization is really interesting because basically we're just trying to use the transistors in a more efficient way. But from a purchaser perspective, this is really interesting because building these is a very cost-intensive process. And so if we're trying to build one of these chips, we need to, at the design level, figure out all of the errors ahead of time. And so we need fast simulation tools to make sure that this is done in a productive and efficient manner. The second part of this is that the computers that we're running on are already being impacted by these end of Moore's law trends. So I was trying to think of the earliest NERSC machine that I could remember, and that was Hopper. So Hopper used to have 24 cores per node, and if we fast forward to today, we have Perlmutter, which has 128 cores per node. So we have a 5x increase in the number of cores per node. And so if we're talking about how can we speed up simulation in order to address these future kind of design challenges, we need to be thinking about how can we effectively leverage the concurrency of these architectures. And so what I'm proposing here today is an alternative synchronization mechanism for SST. So SST is just a common architectural simulator, and by basically changing how we do the parallelization, here we get speedups of 2x to 3.7x. Right, so just a little bit more about SST. SST stands for the Structural Simulation Toolkit. It's being developed out of Sandia, and it's a very popular framework, and it's basically characterized by two main facets. So one is that it's meant to be extensible, and two is it's meant to be scalable. So the way SST works is it provides a bunch of components here. These are basically common hardware devices. So you can think caches, cores, memories, and these all plug into an SST core. In addition to the components provided by SST, you can also plug in your own custom components. So this is the extensible part. If I'm building an AI accelerator, I can drop that in, and it'll interface nicely with the network, so I can figure out what would the performance of, say, a supercomputer with these custom fancy accelerators look like. So the second part of SST is the core. And so the core manages and coordinates all of the events between the different components. So you can imagine if I send a memory request to a cache, I need the core to basically make sure that those events get passed in the correct order. And so just to emphasize what we're trying to do here is we are proposing an alternative parallel backend to the SST core. So I thought I would just give you kind of a brief overview of exactly what these simulations look like and what exactly we're doing. So in the context of computer architecture simulation, we basically split up our simulation state into a bunch of components. So you could imagine you have a CPU, you have a cache, and then you have a memory. And then all of these components are executing time-stamped events. So for example, the core is ticking along, and with a fixed frequency, it might issue a memory request to a cache. So you can see here, for instance, this, and then the cache will bounce that out to the memory, and eventually that'll come back. And so here, with these dashed lines correspond to the events that have been scheduled, but not yet executed. And so the key question that we have is how do we ensure that these events are executed in the correct order. So if, for example, you could imagine that each event here takes the same amount of time, you can see here that the CPU event would be delivered after this kind of cache event. So we have to be kind of cognizant in this parallel discrete event setting of discrepancies between simulation time and wall clock time. And this is particularly difficult in a parallel context where the cache might be, say, on a different process, and you don't want to have to query the CPU all the time or the memory all the time. Hey, do you have any events for me? So this is kind of the broad, big parallel discrete event simulation issue. And so there's basically two ways to address this. The conservative approach, and this is what SST does right now, is it tries to leverage model-specific information to ensure that these causality violations, so executing events in the incorrect timestamp order, can never happen. So what we do in this case is we try to leverage model-specific information about a minimum latency required to send a message between components. So in this very simple case, this delay would be, for instance, the L1 cache latency. And so if we know that a certain delay is associated between any elements, if we synchronize at the start of what's called a look-ahead window, we know that no events will be sent to us within that look-ahead window. And so we can safely execute all events within that window safely in parallel. And this is basically, right, so we need to synchronize here, and then when we get to the end of the look-ahead window, we can synchronize again, and then the look-ahead window moves forward. So in this way, we're basically ensuring that events are never processed out of order. Now, what we're proposing is an optimistic approach. And so the optimistic approach says we'll allow for events to be executed out of order. So in this case, right, to harken back to this example, we have this causality error. So that memory request returning, it has now been executed before the memory request from the cache here has been processed. And so this is exactly what we need to undo. And so what optimistic simulation does is it identifies this, and then we reverse it, and then we replay the events in the correct order. And so in this way, we're able to totally eliminate the synchronizations. Obviously, we have to make sure that our events are reversible, and there's also certain overheads that we have to make sure that we can always reverse these events. So why do we think this is a good idea? And we really here, in this case, in this specific case, look at what these numbers are. So the size of the look-ahead, as I'd mentioned earlier, has to be sized for the smallest latency. So there's like in this case, it's like maybe 4 cycles. But we know if, for example, we're doing a memory-bound application, that the frequency with which these events are being issued from the CPU and with which they're being processed is 1 or 2 orders of magnitude larger. So the look-ahead window is very, very small for the number of events that we would expect to be passed between these different components. And specifically in the context of these kind of, how our computer's changing now, this synchronization that's associated with each of these look-ahead windows now is becoming more and more expensive as we have more and more cores per node. So this is something that is becoming increasingly expensive, and so that crossover point between optimistic and conservative synchronization now shifts in favor of the optimistic synchronization. So now for some results. Here we're simulating a tiled architecture. So this is basically, we have a bunch of tiles that have CPUs and caches, and these are all connected on a network. So this is actually an architecture that's very similar to that Esperanto AI accelerator that I had at the beginning. We are running the stream benchmark. This is a memory-bound benchmark, and so that intuition that I was trying to give you related to the look-ahead window and how frequently these memory requests come through is exactly what's happening in this simulation. The mesh network has a look-ahead of only 100 picoseconds, and this has to do with how the SST developers design their elements, but this is a very small look-ahead. And then the other thing that's worth emphasizing is we don't actually have the ability to roll back these SST element events yet. And so in the case of the SST or the optimistic SST model, we're actually generating an event trace. So we run the real application in serial, and then we figure out which events need to be executed and how long they took, and then we replay that in our optimistic setting and figure out how long it needs to take. So this is the only performance slide that I will show you, but basically what we've done here is we have scaled out both the conservative version of this code and the optimistic version of this code. We've done a strong scaling on a single node of Perlmutter, and we figure out what are the fastest times. So then for each setting here, we break out for each core kind of how was the time spent. So you can, unfortunately, the colors didn't come through, but this tiny green, and I think it's a little bit lighter, version on the bottom is the time spent in the elements. So this is quote unquote our useful work. And the red part that's most of this graph is spent in the core. So that's really, if we're focused on optimizing these codes, we really need to be optimizing the core, and it's not so much about what's going on in the element. The kind of key takeaways from this slide are, so if we look at just raw wall clock time, we see a 3.7x speed up here, just in terms of reduced wall clock time. The other thing that's worth emphasizing is that we only increased the cores by 3 times between these two configurations, but we're seeing a more than 3x speed up. So this means that the optimistic algorithm is actually running even more efficiently. So in terms of like the work times depth, the optimistic algorithm is more efficient in this case. So with that, I'll conclude. Just to reiterate, the key takeaways here is that fast computer architecture simulation is a key technology that we need in a post-Moore computing era, and we believe that optimistic PDES, or parallel discrete event simulation, is kind of the key technology to enable this. So here's a bunch of things I didn't talk about. Here's some next steps, and with that, I'll take any questions.
Do we have questions?
So I'm curious, when you were comparing the 32 versus the 96, did you try your optimistic on 32 just to see whether it did better on 32? Is there a reason why you wouldn't have done that comparison?
Oh, yeah, we did. So the point of that slide, and I can just go back, was to just show what was like the fastest versus the fastest. So in both cases, we did a strong scaling study where we scaled out to the full 128 cores. And then we look at, for the fastest time to solution for both configurations, and they occur at different points, where are we spending our time? So that's what this slide is. We have compared the 32 versus the 32 as well. And it's faster. I don't know what the speed up would be right off the top of my head. There are some, also, I guess this is more than you wanted to know, but there are some interesting things where changes we've made in the core actually slowed down the serial version. So our optimistic code is slower if we compare single core versus single core, but then ultimately those changes at the end result in an improvement in time to solution. If so, in the end here means if we're using more cores as we scale out further.
So the optimistic predominantly matters when you're going to write to memory. Is that the case?
No, the optimistic is really just about eliminating synchronization. So that was just like an example that I used, but the fact that the conservative approach has to do this synchronization every time tends to be really expensive. And if we can eliminate the synchronization and there's certain model-specific behavior that we can exploit, then the optimistic approach will outperform the conservative approach.
Okay, so the part that was missing here is that you must have to model what should have happened if you'd been doing a non-optimistic synchronization and then checking whether or not that is what happened.
So can you?
How do I know whether I got to roll it back or not?
Oh, well, basically what happens is every component here keeps track of its kind of most recently executed event. And so if you're executing an event and that timestamp is lower than where you think you are, you've identified rollback. So what the optimistic approach does is it keeps kind of track of all of the events that have been executed, and then it basically does those. So you kind of incrementally roll back You also have to send out like anti-messages, so any events that you sent out also have to be rolled back, and so you have to undo this process.
Thank you. If you have any other questions, please follow up with Max during our break. Let's thank our speaker once more.